Uh, Good morning to all. I am going to talk about our own sun, where a star with which we live together, and a star which is important to our life on Earth, and a star which is important to many of us, both as a day-to-day life as well as a star which allows us to understand the astronomy as together, including the other stellar systems in our universe.
Sir,
Sorry for the interruption. So we are going to study about a star which is very close to us and which is an important system for our life on Earth. So this picture shows you our universe, and it is a pretty vast universe in which we live in a very small area in the universe. And the universe spans about 27 kiloparsec, which is a distance. It's almost, if you want to travel from south to north of India, you have to travel some 500 crore times to cover this one parsec. And of course, our universe is 27 kiloparsecs. You can see the vastness of the space in this. And we live in a very small area in the universe, somewhere around in one of the arms of this spiral galaxies, which is called as the Milky Way galaxy, which many of you would have seen in the nighttime of nighttime sky observations. And I mean, this universe, we also call this as, we live in a space called the heliosphere. And heliosphere is a space encompassing the solar system, in which the solar wind has a significant influence. That means the wind from the sun, or the influence from the sun, is propagated in the whole of the heliosphere. And this is not new, and we know this similar kind of sphere existing in other stars, which is called as astrospheres, and few of the examples are shown on the right hand side of the figure. And I mean, this talk is not going to the details of the heliosphere. Of course, there are other talks which would be under the START program, which will be covering the other aspects of the heliosphere. This gives you a feel for where we are in the heliosphere, and this is a linear scale in which our solar system exists. And you also see that we also have the interstellar space, which is outside of our heliosphere. And these are all recent observations from the Voyagers, which has crossed our heliosphere and got into this interstellar space. This heliosphere is split into two. One is the inner heliosphere, which typically below 10 astronomical unit, that is the 10 times the distance between the sun and the Earth. And anything above that, we call it as an outer heliosphere. Initially, our understanding was that the sun's influence stops at the heliosphere. I mean, the heliopause, what you see around 100 AU, is where we thought the sun influence, the influence from the sun will stop. It will not propagate outward from the sun. But our recent observations from Voyager has clearly mentioned that the influence of the sun is felt even much above the heliopause. So that means that the influence of the sun is not only contained within the heliosphere, it does reaches outskirts of our heliosphere too. Okay, coming back to the sun, I mean, so it becomes important for us to understand the sun. How does it behave, and keep a watch on the sun for a longer period of time. Why do we study them? And of course, I told you that it's essential for life on Earth. And you know that without solar activities and the sun, most of the energy what we get on the Earth is no more available. In that scenario, we may not be able to live a comfortable life on Earth. And there are conditions in the sun. I mean, of course, it exists in other solar systems too, which we cannot we cannot demonstrate it on the Earth. So those conditions is a kind of a laboratory conditions which we cannot mimic on the Earth. those kind of physics can be studied from these kind of stars. So we call this as an unmanned laboratory. We do study some of these quantum interferences between the atomic levels from some of these spectral lines from the sun, which is very difficult to mimic on the Earth. And many of the elements, for example, helium, is an element which was first found on the sun before it got manufactured on the Earth. And of course, sun is closer to us, so it gives us much more information. So any close objects is easier to study compared to further objects. So we use it to understand other stars, how the other stars behave. Of course, sun-like stars behave can be understood from our own sun. And this is the only star in the universe which can be resolved to greater details. Of course, I mean, there are new techniques and new observations coming up trying to resolve the other stars either directly or indirectly. But with smaller telescopes and smaller effort, we can resolve our own stars with much greater details, and which gives us a lot more information than what other stars can provide. And of course, the influence of the sun is not only the radiations coming from the sun. The sun also influences our Earth's atmosphere, and which can modify our own climate on the Earth. For example, the cloud formations is somewhat indirectly related to the cosmic rays, and the cosmic rays modulations is indirectly related to the solar activity, the cycle of the sun activity. So it does affect Earth's atmosphere, and to understand our own climate, the solar energy input is an important element to many of our solar models. Of course, as a student, I mean, you do go through a lot of physics courses, and many of the courses what you take, what you study during the master's and bachelor's, do link to many of the solar physics aspects. Few of them are listed here. I mean, it's not exhaustive, but few of important physics which you go through during your master's and bachelor's is an important element. For example, atomic and molecular physics, what you study when you form absorption line, when you form emission lines, is an important element for us to study the sun and its related phenomena. Plasma physics, the sun is made of ionized gases, which is nothing but we call it as a plasma. The plasma dynamics is an important element to study the sun. And one aspect of research on the plasma generations in the laboratory, a lot of information is available on the sun. For example, confinement of the plasma is done through magnetic field confinements. And of course, we do see these magnetic field confinement of the plasma on the sun. And one of the biggest challenges what we have on Earth to confine the plasma is to confinement for a longer period. I mean, we are not able to confine them for a longer period. And that has some potential implications of how the magnetic fields and the plasma interact with each other, and whether the magnetic bottles what you create on ground, whether it's good enough to sustain for a longer period is an important research element which is going on, which is actually being done naturally on the sun. So many of these front-end researchers, which is an important element for us to sustain the next energy resources on the ground, is somewhat naturally available on the sun. So studying them gives a lot of important information for us to progress in the technology as well as the understanding of the plasma what we created on ground. This just gives you a kind of a number for you to keep in mind. The mass of the sun, we call it as a one solar mass, it's about 333,000 Earth's mass. And the radius is, we call it as one solar radii, It's equivalent to 109 Earth's radius. That means you can fit in some 109 Earths in the sun's diameter. The average density is about 1.4 gram per centimeter cube, and compare it with the average density of water, which is about 1 gram per centimeter cube. It's not very different. The luminosity is 10 power 26 times. Of course, we're sorry for the numbers because it should be 10 power 26, 3.84 into 10 power 26. The effective temperature is roughly around 6,000 degree Kelvin. That's why when you look at the sun, of course not with the naked eye, it is somewhat yellowish color because the peak wavelength is somewhere around the yellow region. The core temperature is 15 million Kelvin, 15 into 10 power 6 degree Kelvin. And we are typically in the age of, it's about 4.5 gigayears. I mean, the sun is in the middle-aged star. We are in the middle of the lifetime of the sun. Distance is 1 astronomical unit, which is 1.5 to 10 power 8 kilometer. And I mean, the angular size, the 1 arc second is about 700 kilometers. And of course, sun rotates with a rate of 27 days at the equator. And its chemical composition is about most, I mean, 75% is hydrogen. And the next element is helium. And rest of them are all trace elements on the sun. I just go through a bit on the solar structures. I mean, how the sun is made up. Sun has an interior, which we call that anything which you cannot see from the Earth. That is the optical surface, what you see from the Earth. And below that optical surface, we call it as an interior. And it is divided into hydrogen burning core, radiative and convective zones. I will just briefly explain to you what it is. And then the solar atmosphere, it's a directly observable part of the sun, and it is, sorry for the missing element, it's divided into 3 zones, photosphere, chromosphere, and corona. And we also talked about the heliosphere, which is region containing the solar system. Anything above the corona and containing within the solar system, we call it as a heliosphere. This picture depicts it. I mean, what you see here is the core, in interior of the sun, we call it as a core, where the actual energy generation happens. We'll talk a bit more about it, what is the kind of energy generation which is happening. These energy generations, the energy generated in the core is transferred in the form of the photons, the gamma ray photons, and which gets transferred to the surface through radiations in the inner part of the sun interior, and then outer part, maybe about 30% of the outer part, we have a convective layers, which transfers the energy from the inner part to the outer part. I mean, you know that the energy transfer can happen either through radiations or convections or conduction. So in the sun, the inner part is radiative, and the outer 30% of the part is convective. And then what you see outside of the solar photosphere, the visible photosphere, it is all radiative from the surface to by the time it reaches to you. So what is the energy source generation? I mean, as you have studied, it's nothing but the hydrogen fusion into helium, the fusion reactions. And see, 2 neutrons and 2 protons combined together forms the helium, and as well as the light. So it's basically the hydrogen mass, what is there in the core of the sun, is turned into the energy. So it's typically 7 into 10 power 11 kilogram per second of hydrogen is converted into helium every second. And to do that, it does require 15 million degree centigrade. I mean, this is a good exercise which many of your physics students can can work it out. How much of energy needed for you to fuse two hydrogen? That means if I have to bring 2 protons to fuse them together, I have to overcome the electrostatic force between the proton. What is the energy required to bring these two together, to fuse them? If you calculate and use that as the kinetic energy of the two protons and estimate the temperatures, you will reach a temperature of roughly 15 degrees centigrade. So the core of the sun needs to have this 15 million degrees centigrade for it to convert this hydrogen into helium. Then when this helium is produced, you also get gamma rays coming out from it, and you also get neutrons, which is neutrinos, which is coming out from it. And the high energy density and temperatures allows individual protons to ram into each other at sufficient speed. I mean, that is the kinetic energy of these protons to overcome the Coulomb barrier, and that's how it forms the helium atoms and releasing the energy. And of course, the temperature gradients from the solar interior to the surface, we call it as a thermal pressure, which is the one which overcomes the gravitational collapse when the star is formed, and that forms the stability of the star. So the thermal pressure is equivalent to the gravitational force of the sun, and hence the star is very stable with respect to its energy production as well as the lifetime. And this also tells that the energy production rate is an important element for the stability of the star. When the energy production rate starts to diminish, which will happen when the mass it starts to consume more and more, then the star will start to expand, and the core will start to collapse within itself, and that's how the end state of the sun will happen. Of course, it will never happen until another 4 giga years. So we will not be able to see this end state of sun by our lifetime. So this explains a bit more on the nuclear reactions in the core of the sun. Four protons get combined into forms an alpha particles, which is a helium, and of course you also get the neutrinos as well as the photons which comes out of it. This proton-proton chain nuclear reactions, it's about 99% of the energy is produced by the sun, and there is a few, 1% of the energy released in the CNO cycle, which is the carbon, nitrogen, oxygen cycle of nuclear fusion. This is mostly dominant for hotter stars, not for sun. And so throughout the lifetime of the sun, we'll be seeing only the PP chain reactions. So both of these chains put together, 99% and 1%, will provide an energy of something like 26.7 million electron volt, mainly in the form of the gamma radiations, and which is on its way to the surface, which is absorbed and scattered and heats the gas in the medium. And of course, we also get these neutrinos coming from the sun, which doesn't get interacted with anything in the in between and reaches to the Earth. So neutrinos was something which was used to study the reaction rate, the proton-proton reaction rates in the core of the sun, and that is how we confirm the static model of the sun. Of course, when we initially started doing it, the neutrinos were detected using the Homestake neutrino detector systems, which is nothing but 37 chlorine is the chemical composition which is used to have these interactions of neutrino detected. And initially, it was detected about typically 2 neutrinos, whereas the expected is somewhere around 7. So we were falling short by about a factor of 3. So there was a lot of debate on this solar neutrino problem. Why are we detecting much lower than what is supposed to be from the standard solar model? So there is a debate between standard solar model being incorrect, or the neutrino physics is incorrect, or the nuclear physics describing the PP chain reaction is incorrect, or the nuclear physics describing the interactions between the chlorine and neutrino direction is incorrect. So many of these debates were going on in the community between the atomic physics as well as nuclear physics as well as the solar physicists. And finally, the solution was in the missing neutrinos. Neutrinos can come in the 3 different flavors, whereas the home stake experiment was detecting only the electron neutrinos, missing the other 2 neutrinos, the mu1 and tau neutrinos, and hence what you are detecting is 1/3 of the neutrinos. And of course, this this study of this neutrino problem and the solution of this neutrino problem gave Nobel Prize to Davis for his solutions for this solar neutrino problem. So now this neutrino problem is addressed, and we have a fairly good enough standard solar model for us to understand the sun from the nuclear, energy generation point of view. Then comes to the, of course, we have the radiation zone, and the next important interactions happens in the convection zone. So this convection zone is in the outermost 30% of the solar interior. So in this place, the convection sets in, and the energy is transferred to the surface through the convection cells. What you see here is cells of different scales and different sizes. They are the convection cells, which takes the energy from the bottom layers, takes it to the next layer, and that's how the convection carries the energy from the interior to the outer layers. Basically, in this layer, the gas is convectively unstable, and they just these convections goes all the way up to the just below the photosphere. And so from the deeper interior into the core to the surface of the solar atmosphere, the time scales changes because the radiative time scales are different from the convective time scale. Radiative takes about 10⁶ years, whereas the convection takes months. So actually, the photons what we see at the Earth, or what we see now, is actually something like a photons which is released 10⁶ years before at the core of the sun, and at few months at the deeper interior of the convection layers. And of course, what we see is about 8 minutes difference between the photons released from the photosphere to the Earth. How does the convection works? It is a kind of a cartoon which is specified on the left hand side. What you see is stable and unstable convection. You have a bubble of gas, and the density of this bubble of gas is depicted as rho at a height of Z. And when the bubble of gas density, if it is lower than the outside densities, what happens? The bubble of gas feels lighter compared to the surrounding gas medium, so it will start to grow up. It will start to rise in the atmosphere. It will start to rise in the Z direction. So as it starts to rise in the Z directions, if the outside density decreases faster than the density within the bubble, then what you see is after some distance of delta Z, it will again start to feel that it is heavier, so it will go down back into the atmosphere. So that is a stable convection. It will not go up. It will not keep on increasing the gas bubble. Whereas on the right hand side, what you see is an unstable conditions, where as the bubble grows, it will see the outside environment is still lighter. It will still keep on growing, and that is how the gas which is present in the interior will start to transfer its energy to the outside surfaces. So this is an unstable convection, and of course you have seen this convective instability during a water bubble in the system. So when you heat a pan of water, you will see these unstable convections in the system. So what you see here on the right hand side is a photospheric image of the convective system. So what you see here is what we call a granules on the sun, and this granular pattern, what you see is nothing but the convective situations what we see below the surface of the sun. The bright surface is nothing but the gas bubble which is coming up, and the dark lanes what you see between the bright structures is the gas which is going back into the surface. We call that as an intergranular lanes. These are the lanes where the gas will go back to the surface, and the bright regions are the regions where the gas is coming up into the outside atmosphere. How do you study the interior of them? They are studied through helioseismology. It's very similar to the astroseismology or the Earth seismology, where we look at the vibrations of the sun on the surface, and the vibration informations will tell us about the interior structures of the sun. So what you see here on the left hand side is the Doppler measurements. That is, the Doppler measurements is how the sun's surface is moving up and down, which is nothing but the vibrations which is happening interior is propagated into the surfaces, and from these power spectra of these surface measurements, and with the proper modeling of the interior structures, we can study much details about the interior structures of the sun. On the right hand side, you see about many of the waves which is propagating in the interior layers of the sun. Depending on the frequencies of the waves, it can go deeper into very close to the core, or it can trap only in the convective layers. Most of our helioseismic studies will be done with these convective layers frequencies. So we'll be able to see up to the close to the what you call the internal convective layer of the sun. And there are G modes, we call that, which can go very close to the core of the sun, which is being attempted to study with many of these instruments to see the internal details of the sun, which is still yet to be done to much detail, like what we do with the convective layer helioseismology. And to do this, we need to have 24 hours of data, which needs to be observed. I mean, observations of the sun has to be done 24 hours continuously. One way it is done is to have the telescopes put across the globe, so that when we are on the night hand side, somebody else in some other country will be in the day side, where they will be observing the sun. So similar instruments were put across the earth, and to cover the sun observations 24 hours continuously. And we have an instrument placed at Udaipur Solar Observatory, comes under Physical Research Laboratory, PRL, Ahmedabad. It is placed in one of the beautiful lake site of Udaipur, and they are supporting the observations on the helioseismology. This is needed. Continuous observations is essential for us to capture the correct frequencies of these oscillations, so that the amount of information what we get is not missed for us to infer the internal details. And just to give you the glimpse of what is needed, they will be measuring the velocities of the sun, that is the motion of the sun up to a level of 1 centimeters per second. That is the atmosphere, the visible atmosphere of the sun. If it moves by 1 centimeter per second, these instruments will be able to detect that. Longer the time series, it's better. Then you will be able to go to finer and finer frequencies, higher and higher wavelength. You'll be able to go to deeper and deeper wavelengths. So that is something which is being carried out for almost a decade now. We have plenty of data available from this. Of course, I mean, we know that the sun rotates. The rotation rate of the sun, as I told you, it's about 24 days in the equator. And as you go higher and higher in the pole, the rate starts to increase as you go higher. So it's a differential rotation. That means the equator rotates, faster compared to the poles. And this is also seen in the Doppler image of the sun. What you see on the left-hand side, one side is red shifted compared to the other side, which is blue shifted. So the limb which is going away from you is red shifted, and the limb which is coming towards you is blue shifted. That is what is the big thing here. So the differential rotation is an important element for us to see many of these structures. What you see as dark structures on the sun, these are all called as sunspot, and they all formed due to the differential rotations of the sun. We'll come to a bit more details on this in the later slides. So coming to the solar atmosphere is composed of multiple layers, and with the lowest layer is considered as photosphere, and it's called as photosphere because it looks like a sphere, and that is the atmosphere where the photon escapes from the sun, and followed by the chromosphere, the transition region, and the corona. Okay, and we model that is the simplest one as a spherical model, and single component plane parallel atmosphere, and its the density from the solar atmosphere drops exponentially, and that is how you model it. Rho naught is the density in the deeper layer of the photosphere, and as you go in height, which is the height here, the density will start to drop. The drop rate of the density, we call that as a scale height, H rho, which is typically on the photosphere, it's about 100 kilometers for a temperature of 6,000 degrees. The mass of the solar atmosphere, which is the mass of the photosphere, most of the mass is confined to the photosphere. You can compare that mass to the mass of the Indian Ocean. And the mass of the chromosphere is typically the mass of the Earth's atmosphere. It's typical numbers for you to keep in mind. This gives you some information about the different layers of the sun. The photosphere starts somewhere around a height of 0 kilometer, and it has a few hundred kilometers, maybe around 200 to 300 kilometers, and where the temperature minimum starts, and then above that the temperature starts to increase, lower chromosphere, middle chromosphere, and the higher chromosphere. And at the base of the higher chromosphere, the temperature starts to increase drastically, and then at the corona it goes up to a million degree Kelvin. So this region we call this as the transition region, where the temperature starts to increase drastically, very high in the transition region. The photosphere extends between the solar surface and the temperature minimum, and from where most of the solar radiation arises. So we see visible UV and IR part of it comes from the solar photosphere. The temperature varies between 4,000 to 6,000 degree Kelvin, and the temperature decreases outwards. So since the temperature decreases outwards, The photospheric spectra consist of most of the absorption lines. That means the background is hotter compared to the atmospheric constitutions of the photosphere. So the atmosphere starts to absorb the radiations and re-emit it. So that's why you see most of them as absorption spectra. We assume that it's a local thermodynamic equilibrium. That means the temperature is same wherever you see in the atmosphere. The temperature distribution gets neutralized. There is not much gradients in the temperature, and the energy transport is by convection and radiations in this region. And the main structures what you see is the granules, sunspots, and papillae. I'll show you some of these structures in the photosphere. What you see here is the sunspot. What you see, I think, of course, you saw the granular structures when I talked about the convection, and and then you also see this quiet regions where most of the regions, if you zoom in, it's mostly the granular part of it. The sunspots which you see on the sun is, as I told you, it's purely because of this magnetic field, which is anchored in the deep layer of the convection zone. Typically, when the sun is minima, what you see here is dipole structures. You have a north pole and south pole, and the magnetic field lines are wrapped around on the solar atmosphere because of these dipolar structures. And when the sun rotates differentially with equator moving faster compared to the poles, you start to stretch the field lines in a manner we call it as a omega type stretching, and this along with the twist in the convection zone, we start to see the sunspot formation. The south and north polarity formation happens because of this the twist in the inner layers of the convective zone and the differential rotations. We call this as an alpha omega system. Alpha represents the twist in the convection zone, and omega is due to the differential rotations. Alpha omega dynamo creates this particular the sunspot. So as you can see that sunspots will form as a pair. You will have a south and north polarity. You will see two regions associated with any of these sunspots. So you see two of them, south and north, south and north, south and north, like that. Okay. So that's how the sunspot is formed, which is formed on the solar photosphere. If you go with a very high resolutions, you see that there are structures in the sunspot. We call as umbral structures, where you see the darkest regions. Penumbral structures, where you have these the fine structures. What you see on the outer sides of the sunspot. These are all called the penumbral structures. And then the quiet sun regions outside of them, where you see the granules, which is nothing but the convective cells. What you see on the bottom layers. The umbra is cooler compared to the surrounding regions. That is because the convective gas, which is transferring the energy from the deeper layers to the upper layers, gets suppressed in this by the magnetic fields in the umbra, and hence the energy transport through the umbra is much lower compared to the outside areas. That's why it looks darker and cooler compared to the outside areas. And in the penumbra, we also see that there are a lot of flows happening. We call that as a siphon flow. And these flows were discovered by a person called Evershed at our Indian facility, Kodaikanal Solar Observatory. And that is so the discovery of the Evershed flow happened in India, and there is a to commemorate that, there is a to commemorate the 100 years of Evershed effect, which was found sometime in 1906. Our Indian postal system released this particular stamp during that particular period, based on this Evershed effect. Then coming to the chromosphere, the chromosphere start to see different structures, different emissions in the solar atmosphere. And again, you see that you have the dark sunspot, which is still visible in the chromosphere. But apart from that, you also start to see the bright structures surrounding it. We call that as plages surrounding these sunspots. And these are all taken at kind of a 7,000 degree gas in calcium 2K line. And I mean, these are all the emission features in the calcium atomic structures. And as you go higher in the temperatures, say for example 50,000 degree Kelvin, 5 to 10 power 4 degree Kelvin gas, which is a helium ionized gas, you start to see the active regions which are brighter compared to the cooler gas, where you see active regions cooler. So the sun shows different features as you go look at the sun at the different temperatures. And of course, India also has a good good contributions to the helium detections. The helium, as I told you earlier, is detected in one of the solar eclipse when the chromosphere was identified that the pink color structure which is coming from the helium emissions in the chromosphere. So in the chromosphere, energy transport is mainly by radiation and the waves, and of course many of these bright features what you see has some implications from the waves coming from the photosphere. And strong evidence for a spatially and temporally inhomogeneous chromosphere is present besides the gas with temperature of greater than 8%. So there is a good link between the chromospheric structures and the photospheric structures, and I'm just going to demonstrate that in this slide. What you see here on this right-hand side image is the sunspots. You see the sunspots and the granules surrounding it. Definitely, you don't see any plages which you saw in the chromospheric structures. So these structures are from the photosphere, deeper layers in the sun. And as I go higher in the atmosphere, at the chromosphere, you start to see the brighter structures, the plages which starts to appear surrounding the sunspot. So that means once you start to see plages in the structure, that means you are looking at the chromosphere compared to the photosphere. And in the chromosphere, and if I especially look at the limb of the chromosphere, you start to see the very fine structures like a fibril kind of structures. We call them at spicules. And you also see these big structures which you see it everywhere in the chromosphere. They are all called network structures. These are all the network of magnetic fields which form a bigger structures. We call that as a network structures. And you also see prominences in the limbs. You can see that the huge plasma which is standing above the solar atmosphere. And initially when you see that, you'll be puzzled, because how does the plasma gets suspended in the atmosphere when there is a lot of gravitational force which is trying to pull the plasma into the sun, and this is purely due to the magnetic fields. So what you see here is the magnetic loops which is holding the magnetic field, which is holding the plasma within the magnetic bubbles, what you see here. So it is like a magnetic bottle where you hold the plasma inside the magnetic bottle, which doesn't get influenced by the surrounding area. The magnetic field lines protect them from the outside environment. Of course, they also, because of the dynamics of this magnetic field, they also starts to reveal much more interesting intriguing phenomena, and that is what we call this the flares and eruptions. And this movie tells you a lot of magnetic field lines dynamics, which you see, which changes the intensities. The intensity change is nothing but the plasma dynamics. So you see a lot of plasma which is getting connected and disconnected and gets erupted into the interstellar medium. These are all due to the flares and coronal mass ejections. This is a pretty interesting movie, and I mean, of course, if you go into the Soho and on the internet, you will start to see many such movies with a lot of interesting eruptions, which throws the plasma into the interplanetary medium, which has the influences on the Earth as well as the satellite technologies, which is grown in the interplanetary medium. I just run this movie a bit more. You just watch it. There's a lot of interesting phenomenon which goes in this particular day. You also see that's a lot of pebble structures. What you see, the background gets noisy. That's purely because the particles which is ejected into the system reaches the telescope, which is observing this particular event, and these energetic particles deposits energies on the camera, which is looking at it, and these specks what you see during that period is nothing but these energetic particles which comes and hits the detectors. They are the one which you see it as a background noisy system which comes in. Okay, then comes the transition region, which we talked about it. The transition region starts somewhere around 2000 kilometer, which is in the base of the chromosphere, and goes all the way up to the corona. And you see that the temperature from say 10,000 degree to goes all the way up to million degree over a very short scale heights. And many of these lines, emission lines, form in this particular different temperatures. So we use these emission line features to study them, how these different temperatures, how this atmosphere behaves at the different heights and different temperatures. What you see here is a typical image from a transition regions. If I look at the lower transition regions of the order of say 10,000 degree Kelvin, it looks like this. It looks very quiet. And if I look at the upper transition regions, you start to see all kinds of structures. When you see the active regions, which are bright in structures, you see the quiet regions, which doesn't have much activity, but they are still brighter, but it's not as bright as the active regions. And we also see in this background quiet regions, we also see some of this bright small speck kind of stuff. You see it here, you see it here. We call that as X-ray bright points because these were all seen in the X-ray images of the sun to start up with. And they're all small scale magnetic fields which are deep rooted in the solar photosphere. And we also see these very dark regions. We call this as a coronal holes, as if nothing is there in there, and they are an important element of the solar wind. And these are the regions where the fast solar wind comes in. The solar wind has two dimensions. One is the slow solar wind and the fast solar wind. And these are the regions where the fast solar wind comes. They are very important for the space weather events because the fast solar wind reaches the Earth faster, as well as it has energetic particles which can couple to the Earth's atmosphere much easier compared to the slow solar wind. You will learn about this space weather and interactions in some other lectures during the STAR program. And you also see these active regions arcades in there, which is also seen in the upper coronal regions, in upper chromosphere regions. Then, of course, comes this corona, which most of you would have seen in the during the eclipse periods. You see a very beautiful structures of the corona, which mimics the magnetic field structures, which is in the photosphere. And we also see this million degree corona in the extreme ultraviolet images taken at 195 angstrom wavelength. So the corona is created due to the magnetic fields of on the photosphere, and the structures of the corona do vary with the magnetic field structures what you see on the And of course, the magnetic activities, do vary over the solar cycle. So what you see here is a butterfly diagram. If I take the number of sunspots, what I see on the sun, say for example, if I count if we go back, if I count the number of sunspots on any particular day on the solar disk, and then plot them. I mean, these are all some simple projects many of you guys can easily do. The data is available. If I plot the number of sunspots seen on a month or a year, average number of sunspots seen on a year, and plot them over many years, you will start to see this beautiful structure. We call it the butterfly diagram. What it shows is that when the new cycle, when the new activity starts, it starts at the higher latitudes, say plus or minus 30 degrees, and then slowly drifts towards the equator. And then it dies off, and then the next cycle starts at the plus or minus 30 degree latitude. This has a profound implications of our understanding about the dynamo, and any dynamo theory has to depict or has to produce this butterfly diagram for us to really understand for us to really appreciate the dynamo mechanisms. So it basically says that you have a typically 11-year solar activities. That means every 11 years, the solar activity increases and decreases and increases and decreases. That's how it goes on. So, so it's a 11-year period is the period of the cycle. What you start to see is equatorial drift of the active regions, and then you will start to see the active region dies closer to the 30 degree latitude, which gets drifted into the poles of that. And we also have this Hale's polarity law and Joyce law. I would urge you to go back and read about it. They have a very important implications on the solar dynamo, and there is also something called a 22-year magnetic cycle. That means the flipping of the magnetic field lines of the sun, like Earth magnetic field line flipping. Sun also flip its north and south every 22 years. This gives you a picture of the 11-year cycle in X-rays. You see that when the sun is minima, you don't see any activities in the coronal regions. I mean, this is X-rays actually images the corona, so you don't see much activity in the corona. As you start to see more and more active regions, you start to see the plenty of activity on the corona. So this basically tells you that the magnetic field is the one which in the photosphere is the one which provides you a lot of activities in the chromospheric and the coronal regions. And what you see in this very beautiful structured plasma is all due to the magnetic field lines which is on the photosphere. So I think I will complete with a statement that sun is very dynamic, and sun carries a lot of what you call plasma, which throws into the interplanetary medium, and they do propagate in the interplanetary medium, as is seen in this particular movie, which is observed from our own OT radio telescope. There is a disturbances which starts from the sun and propagate in the interplanetary medium, and that is how your subsequent lectures will start to cover this the link between the sun and the earth, and as well as the other planetary systems during the course of the START program. I will stop here and take up any questions from the. Thank you.